So in this section, we'll look at the total probability theorem, which gives us a way to calculate the probability of an event when we really only know the probability of different events within it. So let's say that we have a sample space partitioned into different areas. Again, it's a partition. And assume further that we have a probability a sub I for each of those ith partitions, and then a probability of some event b, given that we're in that partition, given a sub I, for every partition. And let's say that we want to find the probability of b. Well, the probability of b would be the probability of b intersected with each of those individual partitions all summed together. Remember, the important part about a partition is that they can't overlap and that they can't share elements. But every element is included. Now, to look at this graphically, let's say that we have a specific sample space where there are only three partitions, a sub 1, a sub 2, and a sub 3, and that each of those partitions shares some aspect of the event b. Well, if we want to find the probability of b, what we really need is the probability of a sub 1 intersected with b plus the probability of a sub 2 intersected with b, all the way out to the probability of a sub n intersected with b for however many a sub i's there are. We'll assume there are n of them. Now, if we utilize conditional probabilities, we can rewrite this a little bit, and we can say that the probability of b is actually equal to the probability of a sub I multiplied by the probability of b given a sub I for all i's. So in the case above, it would be the probability of a sub 1 multiplied by the probability of b conditioned on a sub 1, then the same thing for a sub 2, and then the same thing for a sub 3, all added together. Now, another way to look at this and kind of reinforce that this works is through a tree diagram, right? If we've said that this is the probability here of a sub 1, and this is the probability of a sub 2, and the probability of a sub 3, then we know that this is the probability of b given a sub 1, probability of b given a sub 2, and the probability of b given a sub 3. And these eventually turn into the intersections out here on the right-hand side, as we saw in our previous section on the multiplication rule. So given that we can sum all three of those together, we ultimately can convince ourselves that this equation here, summed over all I, is correct, that that is going to give us the probability of b. Now, why is this important? Well, ultimately, we can say that the probability of a sub I, we can kind of view as a weight. We can view this as weighted averages. But to generalize this and formalize this, we can say that the probability of b is just equal, again, to the sum over all I of the probability of a sub I multiplied by the probability of b given a sub I. So to look at an example of this and actually put some numbers to it, let's say that we have a bowl, and in that bowl we have 3 apples and 4 oranges. And let's say we've got 2 guys, Bob and Steve. And Bob comes up and selects a fruit from that bowl, one of the apples or the oranges, we really don't know. And then shortly after, Steve also selects a fruit. Then let's give some event names to this. We'll say B sub A is the event that Bob picks an apple, B sub O that he picks an orange, and then S sub A is the event that Steve picks an apple, and S sub O that he picks an orange. Again, just throwing some labels on these. So based on this situation, again, the bowl has 3 apples and 4 oranges. What is the probability that Steve picks an apple? Well, let's go through and figure out using what we know. So the first thing we can do is just start writing some stuff down. And let's say The first thing that happens is that Bob is going to pick a fruit. So let's see what the probabilities of him picking an apple and an orange are. So the probability of Bob selecting an apple is equal to 3 out of 7. There are 3 apples and 7 total fruits. Again, we'll assume that these fruits are equally likely to be selected. We can also say that the probability of Bob selecting an orange is equal to the other part of that. It's 4 out of 7. But now we need to start looking at some conditions. And the question that we're asking is, what happens, or what's the probability that Steve picks an apple? So what we can do is use our total probability theorem from before and say, well, what's the probability that Steve picks an apple conditioned on each of these 2 events? If you're struggling with this a little bit, let's draw out a tree diagram. We've got 2 possible paths here. We have the Bob picking an apple and Bob picking an orange. And then from there, we have Steve picking an apple, Steve picking an orange. Again, Steve picking an apple, Steve picking an orange. And what we're interested in here is the probability that Steve picks an apple. So we care about this leaf and this leaf. We don't care about the other 2. So we need to know the probability that Bob picked an apple and the probability that Bob picked an orange. And as you might recall, these are conditional probabilities. So we need to know the probability that Steve picked an apple given that Bob picked an orange, and the probability that Steve picked an apple given that Bob picked an apple. So if we go ahead and calculate those, we'll find that the probability that Steve picks an apple given that Bob picked an apple is equal to 1 out of 3. Now, if we look at this, we can go through and say if Bob picked an apple, I now have 2 apples and 4 oranges. It's a 1 out of 3 probability. Now, on the other end, if Bob picked an orange, then the probability of Steve picking an apple, conditioned on Bob picking an orange, is equal to, well, Bob picked an orange, so we're now 3 oranges instead of 4. So it's 1/2. So with all of this knowledge, we can go back and use our total probability theorem and sum across all of these events to find our leaves. And what that leaves us with is that we need the probability of Bob picking an apple multiplied by the probability of Steve picking an apple conditioned on Bob first picking an apple. And then we will add that to the probability that Bob picked an orange multiplied by the probability that Steve picked an apple conditioned on the fact that Bob picked his orange. And with that, we can plug in some numbers, because this is ultimately, by total probability theorem, our question we're after, the probability that Steve picked an apple, the probability of B. So in this situation, plugging in numbers, we're going to have 3 out of 7, the probability that Bob picked an apple, multiplied by 1/3, the probability that Steve later picked an apple, and we will add that to the probability that Bob picked an orange, which was 4/7, multiplied by the probability that Steve picked an apple after Bob picked an orange, which is 1/2. Again, just plugging in the numbers we just calculated. When we sum those together, we find that this is equal to 3 out of 7. Now you may be looking at that and saying, okay, so there's a 3 out of 7 chance that Steve picks an apple just overall. And then you may look at the problem statement that the bowl has 3 apples and 4 oranges and say, so Bob picked an apple or Bob picked an orange, But at the end of the day, regardless of what Bob picked, there's still a 3 out of 7 chance if Bob hadn't picked anything that Steve would pick up an apple, right? If Bob never came by, the probability of Steve picking up an apple would be 3 out of 7. And this is kind of hinting towards what we'll be covering in our second lecture this week, independence, when the outcome of a first event, the probability of what Bob's picking, an apple or an orange, ultimately has no impact in the final probability, the probability that Steve picks an apple.